All right, let's get started. Hi, everyone. Thanks so much for coming to our conference. Very pleased to meet all of you all. I see that you've are logging in from across the world. I see people from New Jersey, Rochester, as well as from Mexico and India and Nigeria. So welcome. We're kicking off the session with the fireside chat with Anima. Anima, as most of you all know, is a Caltech Bren Professor. Colin White is going to introduce her in more detail. Colin is head of research at Abacus. They're going to be talking about deep learning. Let's get started without further ado. Colin, take it away. And please feel free to also look at some questions from the chat room and as desired, ask the questions which make sense to Anima. Thank you.
Thanks, Bindu. I'm very excited today to be joined by Anima Anandkumar. She is a Bren Professor at Caltech and a Director of Machine Learning at NVIDIA. Anima's research has won numerous awards, including the Sloan Fellowship, the NSF Career Award, and faculty fellowships from Microsoft, Google, and Adobe. So Anima, thank you for joining us today. Where are you taking this call from?
Yeah, thanks for having me, Colin and Bindu. It's great to be here and great to see people join from all over the world. I'm actually back at my Caltech office just this week. Once we are all vaccinated now, we are now slowly heading back. And it's great to, see things go back, but also take the lessons we've learned during the pandemic into our lives. So really excited to see how this summer is going to shape up. How about you?
Great to hear it. Yeah, I'm taking this call from San Francisco, right by Golden Gate Park. On the one hand, I wish this event was in person, but on the other hand, as Bindu said, it's pretty cool that people are joining us from all over the world. All right, so today the topic is the past, present, and future of deep learning. So I thought I would, the topic of this session, that is, and I thought I would go in chronological order. So I have a few questions about the history of deep learning. Maybe I'll start with a pretty broad question. What do you think are some of the biggest factors in the reason that deep learning became so successful over the last decade?
Yeah, it's really been exciting to be an AI researcher over the last decade. The progress has just happened so quickly, right? And so much practical impact in real world domains, including what you and Bindu are doing. Great to see that being productionized and making impact in enterprises and lots of domains. What started this revolution is what I call the Trinity of AI. So, a lot of press and focus is on deep learning algorithms, right? Like neural networks are amazing. I mean, they are flexible. They are, having the ability to learn features directly from data. And there was a lot of excitement even in the 80s and before that. But what was missing in the previous attempts to use AI in a practical way was the absence of the internet and absence of enough computing power. And so the trinity of what caused this current deep learning revolution over the last decade is coming together of large-scale data sets, compute infrastructure, in particular NVIDIA GPUs, where we have very efficient parallelized primitives for matrix operations, and neural networks that can utilize these matrix operations, that are made up of simple units, that are made up of simple operations like matrix multiplications. So coming together of these three realms, data, neural network algorithms, and GPU infrastructure, this trinity of AI is what led to the deep learning revolution.
I see, it makes a lot of sense. Yeah, data. There's been a lot more data in recent times, a lot more compute power, and then of course the research side, the neural network algorithms.
Yeah, and that's where, I really want to, give credit to Professor Fei-Fei Li, her vision to focus on creating data sets much before anyone thought that was important, right? Like she had a lot of pushback. If you read her interviews, she also talks about where her proposals were rejected and people thought this is not an intellectual endeavor. Because many times we, I think, give ourselves a lot of credit that, oh, we can figure out a model for this domain, or we can design really smart algorithms, right? But what proved to be game changing is let the data drive the learning of features, let the data drive what are the features that are useful for, say, image classification. So in such complex domains like natural images, language, or speech, it's really, really hard for us to figure out what are the features that can capture all the variations we see in these natural domains.
I see. That's a great point. Yeah. And Fei Li, of course, created probably the most famous deep learning data set with ImageNet.
Absolutely.
And definitely has driven progress in AI much quicker. And yeah, and also the rise of GPUs. I think that they've become a lot more sophisticated recently, and I think NVIDIA has played a large role in that.
Yeah, it's been exciting to be part of this journey at NVIDIA. I've been a fan since forever, right? We're all, I guess the first time we got to know about NVIDIA was perhaps through gaming and graphics. And even then, you can see how NVIDIA stood out from so many companies in the 2000s that aim to accelerate graphics. But what made NVIDIA unique was to invest in the CUDA platform. In fact, Jensen likes to tell the story where the day CUDA was launched, Wall Street, did not like that path, and the stock went down quite a bit because I think the aspect of why invest so much in a broad platform, whereas you can kind of focus on just accelerating graphics was the kind of right wisdom of those times. But I think the vision of Jensen and others at NVIDIA at that time to make GPU programming democratized, to be able to easily have programmers look for new applications. I think that has been really critical. My colleague, Peter Schroeder here at Caltech, he taught the first GPU programming class, and he says like with the availability of CUDA, there was just so much more activity. And so that's where, you create the ability for people to innovate. And so from graphics, we moved to high performance computing, all kinds of scientific simulations using GPUs. And so that led to creation of, what made that possible was linear algebraic primitives, right? Matrix operations being highly parallelized on GPUs and being upgraded with each new generation of GPUs. And so when the deep learning revolution was starting, when ImageNet Challenge was launched, and as you know, like Jeff Hinton and his students were thinking about bringing back neural networks, they figured out, oh, there are GPUs available with matrix operations. So let's use them to scale up neural networks. And that was really critical because they don't work at small scale, right? At least back then. I mean, we're now thinking of better algorithmic techniques where we can make the neural networks smaller. But for that beginning spark to occur, you needed the primitives that are sufficiently parallelized and efficient. And that's what led to the creation of this deep learning revolution.
Mm-hmm. It's very interesting to hear your thoughts on this history. Yeah, with CUDA sort of democratizing GPU algorithms, and Jeff Hinton and his students realizing that now they can bring back neural networks, which might work much better when they can put them on these high-powered GPUs. I also started to notice a bit of a trend with NVIDIA getting a bit of pushback from CUDA, and then earlier you mentioned Fei Li getting pushback from trying to focus on data. So maybe but it's not always the most obvious thing that'll be the most influential in the long term.
Yeah, and I think this is what I tell my students and junior colleagues is not to take every rejection to heart or not to believe all the criticisms you receive, right? I mean, some of them could be valid. I mean, when Jan LeCun tells stories of how people didn't believe in neural network in the 80s, there was some justification to it because they were just not working, right? So back then, even the world's most powerful supercomputer was less powerful than our iPhone today. So we were just not at the right time back then, and now we are. So I think, sometimes it's also a matter of timing, right? You have to wait for many things to converge together to make an algorithm work or a technology work. But at the same time, you also want to keep pushing ahead if you believe in a vision.
Yeah, definitely. That reminds me of this quote. I forget who the quote's by, but deep neural networks were taken much less seriously a decade ago. And somebody said, neural networks are the second best thing for any problem. And now I think back and now neural networks are the best technique for any problem.
Well, most problems maybe. And
most problems, yeah.
I think, and that's also a matter of terminology, right? Like, what do you call a neural network? If you add in different priors from a domain, different kind of features that you already know work well, a hybrid model like that, would you call it a neural network? Would you call it something else? I think the fact is it's so general that everything else mostly could be brought into this realm. So in that sense, I think the flexibility of it is what makes it truly compelling.
Yeah, that's a good point. Yeah, maybe the best techniques are hybrids where we take in domain knowledge and also use the power of neural networks. So yeah, I guess we've talked a lot about two of the pieces of the Trinity so far. I think the third one you mentioned are the actual neural network algorithms themselves. And so I wanted to ask you about tensor algorithms, because I know that you've done quite a lot of work and have seminal papers on them. So can you maybe start with what tensor algorithms are and why they're so important to the success of deep learning?
Thank you, Colin. And indeed, tensors are a lot more familiar to people now. TensorFlow is the most popular deep learning framework, although other ones are catching up. And we have tensor cores where you can speed up deep learning on GPUs by doing very efficient, even low precision operations. But if you think about what precisely is a tensor, right, it's extending matrices to more dimensions. So I talked about how for the deep learning revolution, having very efficient matrix operations was a key foundation, because neural network layers, you can simply express them as matrix multiplications or other simple matrix operations. And you're composing this with certain nonlinearity and doing many layers of that. And the question is, why just limit to matrices? Our data is not two-dimensional. In many cases, it lives in many dimensions. Right? I mean, if you're thinking of video data, it's images with time, so it's 4 dimensions. If you think about colored video or hyperspectral videos, right, there's even more dimensions. And if you're thinking of autonomous driving, you have LiDAR and vision and sensors. So a lot of data we will see in future will be highly multidimensional. And so the aspect of kind of trying to bring them down all into 2 dimensions and bringing that through a neural network seems very wasteful. Like you're removing a lot of inductive bias that's present in these data sets. And so what tensors do is give you now additional flexibility to not just compute in 2 dimensions, but in many dimensions. So I've talked about matrix products. You can now extend that to many dimensions, right? You can now think about manipulating tensors instead. 3 dimensions, I can picture that as a cube. More dimensions, right? You cannot picture it, but you can still define operations on them. And so there are many benefits to using tensors. So what got me started with this area, which again kind of was a really a chance encounter. I had probably seen tensors in my undergraduate class on quantum mechanics, right? I think that's probably the most common way to get into tensors, and then forgotten about them. And around 2012, we were, so it was me, Daniel Shu, and Sham Kakade. We were discussing the use of efficient techniques for learning variety of probabilistic models, hidden Markov models, topic models. And these are all hard unsupervised learning problems, meaning you don't have label data available. For instance, think of categorizing text documents. At a large scale, you can't possibly label all topics in each document, right? This is very expensive to do and requires careful human reading to do that. So instead, we asked, what if you can directly get these patterns from data itself and learn the topics? And to do that, you can think of simple probabilistic models of how topics can lead to different word generation. And, so you can build these models. But how do you learn? Unsupervised learning is a hard problem. And we were exploring simple matrix methods, like looking at the eigenspectrum of the matrix, and intuitively, most energy is present in dominant topics, right? Like the most, the simplest example is, say, the principal component analysis, or PCA, where you look at where the signal is, what are the most dominant components of the signal. And then we asked ourselves, why limit to just matrices? Why not look at higher dimensions so that we can glean more patterns from such operations? And so think of like now looking at co-occurrence of many words together in a document, and that will give you more intuition of what should be the topics, right? So to give you a simple example, let's say the word apple occurs a lot in a document. If I only told you this information, you're not sure whether it's a fruit or it's the company. Let's say apple and orange occur together. Maybe it's fruit, but orange is also a company, right? What about more words? If you had apple, orange, banana, and others occur together, if I told you that information, you're now fairly sure it's about fruits. So this co-occurrence relationship of many words together gives us the notion of what topics are. And so that's what tensors were great to model, this higher order relationships in data. And so that's what got us started, that these are still very efficient. They're parallelizable. In fact, on GPUs, you can make them even more efficient compared to matrix operations, which is what we are doing now. And so again, it was an unexpected connection of how tensors can be very effective for unsupervised learning of probabilistic models. And now, with the deep learning revolution maturing, what we are investigating is how we can have layers of tensor processing, and so create neural networks that are much more compressed, because these operations have better inductive bias. So you can do it with smaller networks that are more robust, that are generalizable, and also faster, because you can build more efficient GPU primitives for this. And so Tensorly, that is Tensor with LY in the end, is an open source framework we are building where we want to democratize. Again, the theme is always democratization that I see, and go check out the open source framework. There are lots of helpful notebooks, and you can quickly define layers for what tensor operations and create all kinds of new neural network architectures. And so that, I think, has been to me a great journey, like thinking about tensors as a concept to now making them highly practical and efficient for all kinds of neural network models.
Fascinating to hear about the story behind your tensor intuition coming from quantum mechanics, and then realizing that they can be applied in this natural language setting to group all the words together in more dimensions, and then how they were a perfect fit for GPUs. And yeah, I definitely encourage checking out Tensorly. Is this is this something we can use for any sort of application, like natural language data, image data, or anything we want?
Yeah, so the idea is it connects to different backends, including PyTorch. So you can take your existing PyTorch model, and then, if you want to replace a matrix layer with tensors, right? So you can kind of define this new layer very easily, and then aim to compress with it. And so it gives you a way to explore different neural network architectures, even using existing code.
Got it. Makes sense. All right. I think I saw a couple of questions in the chat. One person asked, can we use tensors to deal with graph data efficiently?
Yeah, and in fact, there is another open source framework we are building called Minkowski engine, which is great for sparse tensor convolutions. So like LiDAR data or all the 3D vision data we see, right, tends to be also sparse because, you're looking at a geometric shape, right? There's a lot of empty space where it's all zeros. And so we have made those efficient on GPUs. So I encourage you to also check that out if sparsity specifically is something you want to exploit.
I see. Very interesting. And somebody else asked, what is your favorite course or resource to learn even more about all these things?
The Tensorly has notebooks available, so that's a great way to prototype and kind of have sample codes available. And it also has some helpful graphics and visualization of what tensor operations are doing. So I encourage to start there. We also have a book by Now Monograph that's freely available on spectral methods on matrices and tensors. So that's, again, if you want to, like, from ground up, understand how you can extend matrices to tensors and how you can use it in different applications. I think that's a great resource as well.
Mm-hmm. All right, great. Well, this is already a good segue into talking more about present day deep learning. So you've already mentioned Tensorly and Minkowski engine. I wanted to ask you sort of a very broad question again. And what are some of the most exciting research you're working on at Caltech and NVIDIA? I know you have quite a lot of different threads going. But,
yeah, thank you, Colin. It's been really exciting times, to be both in academia and industry and look at synergistic collaborations and intersections, and also having team of students and researchers from many different backgrounds and interests. So on the Caltech side, I'm very excited about the AI for Science initiative that I co-founded with Isong Yu here. And the idea is, how can we not just use AI in scientific domains, but innovate on AI, right? A lot of AI progress we've seen today is with supervised learning, is with the case where the training and testing data are from the same distribution. But so many real world challenges, especially scientific applications, require generalization that is much more challenging. For instance, if you're thinking of discovering new drugs, you want to predict properties of new molecules that is not tested, right? You don't know all the properties of it, and it's probably not represented well in your training data. And so that's why we need to also work with domain experts and understand what are the challenges in this domain, right? What kind of knowledge can we bring in? What kind of priors can we add? And what kind of flexibility can we use with data-driven neural networks? And so we've been doing this in the realm of drug discovery, going to the foundations, thinking about, if you want to compute the Schrodinger's equation. So that's the fundamental equation that governs the quantum properties of molecules. If you can predict the energy, right, of the Hamiltonian system, then you can predict all the properties, right? So going to that foundation and asking traditional methods, which are brute force, are very expensive. So can we train neural networks to replace them and speed them up, and at the same time maintain the fidelity? So train on small molecules and directly test on large molecules like proteins. Because training on large molecules would be infeasible because you can't get a lot of ground truth data, because these simulations are extremely expensive. Even on a supercomputer, it's not feasible to do it on the largest molecules like proteins. So that's where I think there are interesting questions. And what we've found is this domain expertise, Tom Miller, who's professor of chemistry at Caltech, and combining it with graph neural networks and other deep learning efficient frameworks and scaling them up helps us achieve this goal. We are now able to have neural network models that are 1,000 times faster while still giving really high predictive capabilities on drug-like molecules and so on. So that's one example of what I see as AI for science, working very closely with domain experts, being able to understand, right, have this common language of how to frame the problem and what's kind of more, right, folk knowledge in that domain that's not easily encoded in math, but is important to make it work. And so I think that kind of collaborations can be very fruitful. And what we've seen is another setting where this has been very exciting is solving partial differential equations. So another project here, we've seen very promising results where we are able to solve for the first time using neural networks, Navier-Stokes equations with the same fidelity, almost the same fidelity as traditional methods, while being 1,000 times faster. So if you're aware, Navier-Stokes equation has high fluid, right? It models fluid turbulence. So it's multi-scale, it's very complex to capture, right, from kind of these small eddy currents to global correlations and to predict how it's going to change over time. And so we've been working on these challenging cases of turbulence and now looking at all kinds of exciting collaborations, for instance, with Formula One, with the Lawrence Berkeley lab. So all these places where they have rich data sets, challenging problems in turbulence, right? Climate change is another one where this will be very effective, and we are working with experts there. And so this is where I really find it fulfilling to develop fundamental methods, but have that be taken all the way to making an impact in these domains. And it's a feedback loop, because when it's too challenging to solve a problem, you realize you have to come up with better models. And in the case of fluid turbulence, what made these work was an entirely new framework for designing neural networks for continuous domains. So, because you're defining these equations which map infinite dimensional inputs to outputs, right? Because it can be any arbitrary continuous set from the input to the output you want to map. And so we've come up with a new framework that extends neural networks to these infinite domains. And so having that foundation and then making them efficient, say using Fourier transforms, has made these networks practical as well. So I see a lot of value of building a strong foundation and then asking how to make them practical and lightweight enough to be working on real data sets. So that's on the Caltech side. On the NVIDIA side, I know this is a lot of different things happening. And I think on the NVIDIA side, what has been great is many of these projects, we're also collaborating with NVIDIA engineers to scale them up on Selene and other supercomputers, right, like Summit. So how do we go from a concept all the way to supercomputing scale to solve hard scientific problems like climate change and drug discovery? And the other side of the coin is, how do we now get AI to be much more robust in applications like robotics, where we don't have a lot of training data. And so that's where the use of synthetic data and simulations has been the key. And so NVIDIA, with its background in graphics and simulations, is great in terms of having GPU accelerated physics engines, photorealistic rendering, right? And creating very high quality simulation data And then asking, how do we go from training in simulations at scale, let's say different forms of reinforcement learning in simulations, to the real world, onto robots, could be walking robots, could be arm manipulation. So all these challenging tasks, how do we train in simulation and go to the real world? So that's a central theme in terms of how we can make use of the powerful capabilities of graphics and simulations at NVIDIA and design good algorithms for reinforcement learning and domain adaptation.
Wow, really fascinating things. Yeah, it was really interesting hearing about the AI for science, like I guess sort of interdisciplinary AI endeavor where you take in domain experts from different areas in order to solve, in order to model drug molecules and solve the Navier-Stokes equation. It really spoke to me. In fact, back in my PhD, my advisor, Nina Balkin at CMU, she was also a big proponent of interdisciplinary research. She had this great story once where she was at an economics conference presenting a paper, and someone came up to her and said, "Oh, you just solved an open problem in economics," and she hadn't even realized. So I think, yeah, what you said before about how like everyone in their own field has their own, every field has its own language of talking about different concepts, and really getting two experts together and sort of figuring out the different language for the tools and applying them to different problems can be very very worthwhile.
Yeah, absolutely. And Nina has made a lot of fundamental contributions, right, in this interdisciplinary area of economics and theoretical computer science. So certainly.
Yeah, and also what you said about NVIDIA research with sort of getting problems up to the supercomputer scale and having simulations, going from simulations to the real world. All right, so let me see. I have a couple other notes about current day deep learning. One thing I wanted to ask you is, I know you've had some collaboration at Caltech with neuroscientists or neuroscience professors. So sort of a broad question, but would you be able to talk a little bit about this?
Yeah, absolutely. I mean, what better inspiration than our own brains, right, to design AI? But at the same time, it's hugely challenging because, fundamentally, it's so different, right? I mean, we've had millions of years of evolution that has forced a certain structure and that has forced all kinds of priors into our intelligence mechanisms. So to me, I think, the aspect of trying to do biologically plausible learning, I think is extremely hard. But the philosophy I take is, can I get inspiration of different kinds, right? It could be at a very high level in terms of what's the outcome of a certain mechanism. Can we try to build that into our neural networks? So one example that has really fascinated me is the feedback mechanisms. When you're now watching me and others on the screen, right? It's not just a feed forward processing. So indeed, from the retina, we are going, the signal is going into the visual cortex and the layers there, right? So there is hierarchical feed forward step. But then on top of it, we have the feedback. We have an internal model, so the signals from IT cortex, and even some people have theorized from all across the brain, there's signals that are fed back before we perceive what's on the screen. And in fact, research has shown that if you force people to say what's in an image before the feedback kicks in, they're very error prone. They could be almost like only having 60% accuracy or so. So humans are not robust without feedback mechanisms. And our current neural networks don't have feedback. So I think that aspect inspired us to ask, can we build practical feedback mechanisms, right? And notions of generative modeling that can help us have zero-shot robustness. So even if you've not seen noisy examples during training, at test time, can you automatically try to denoise and figure out what's in the image? And we do find that's the case, and we've seen promising results of inherent robustness with the use of feedback mechanism. And I believe this will be critical for, let's say, autonomous driving and other safety critical applications, right? Because we also want the awareness of what's unknown, what's the uncertainty, right? So I think that's what is lacking in the current models. And it's theorized that our awareness of the surroundings, our consciousness is driven by feedback. So I think that can be a very exciting question in terms of how to make this practical enough at scale. And we're investigating many mechanisms such as, what kind of GANs can we use? What level of generative modeling do we need? And how do we feed that back into our predictive models? So that's one area where with Dorisao, I've learned a lot in terms of what's known there and what's still very unknown in terms of our own brain mechanisms. Another area where I've been very excited about is the use of low power neural networks, right? I mean, our brain utilizes much less power than a GPU. So how can we do this? And it turns out at least one set of experiments hypothesized that the brain is able to store information very efficiently in a logarithmic number system. So meaning you only store the exponent, you discard the mantissa. But that's not how our floating point number systems work, right? We have a long mantissa. And in fact, the FP32, right, requires a lot of, your initial neural networks we thought required a lot of precision. But over time, we've reduced that precision. And so what we did was to train entirely in this logarithmic number system without ever converting to high precision networks, even for back propagation, even for training. And so we designed better optimization methods for this to directly optimize in the logarithmic space. And I think we've, and we can show like energy savings that is 20 times better than the current neural network training. So I think to me, even just the high level inspiration and some experiments we have in neuroscience can drive us towards creating much more efficient neural networks that are more robust, that are low powered, that are generalizable to a much better extent.
Once again, very interesting, both the work on feedback mechanisms with Dorisao and also what you just talked about with the low precision, that we only need the power of all the numbers the neural networks are computing. And I didn't realize that. So that's intuition that comes from neuroscience. Our brains are actually just computing in log scale.
At least that's one theory, right? As in neuroscience, everything is still not completely certain, but one set of experiments suggest that.
That's really interesting. I wonder if in the future we'll scale up to larger architectures and lower fidelity for the actual numbers floating around in them.
Yeah, that's my prediction. I think we need a lot less. And it also depends on the application, right? If you're thinking of an edge sensor that only needs to detect the presence of somebody walking by, you don't need a lot of precision. You don't need a big model. So it would also crucially depend on what our goal is. I think this will be very critical for edge devices, which don't need a lot of intelligence or bigger models, but maybe need retraining quickly as the environment changes.
Yeah, it also reminds me of some of the work we've been working on at Abacus around neural architecture search, where a big question there is how to predict the performance of a neural network before you spend hours and hours of training it. And there's quite a lot of ways to do this, but one of the more interesting techniques that just came out a year ago is taking a single mini batch of data and just looking at what sort of activations what sort of activations are turned on from that single mini batch of data, which you can sort of think of as like the lowest fidelity version of these neural networks. So even from like just a single bit of information from each ReLU, we can have a reasonable approximation of the performance of the neural net.
Yeah, absolutely. And again, if you see, our brains are so plastic, right? When people have brain injuries or accidents, in many cases, you see the ability to, even if they've lost part of the brain, they can, over time, regain a lot of functionality. There are cases where people are born without a cerebellum and are able to do just fine. So even our current theories of what specialization occurs in the brain, I think a lot of it is still unknown on terms of how we can have this incredible plasticity even into adulthood in many cases.
Very exciting. So I guess we have about 5 more minutes left in the session before we hand it off to some other exciting panelists. And I guess so far we haven't really touched on the third topic, which is the future of AI. So one question I wanted to ask you is to bring it back from the start of the talk when you talked about the trinity of data, compute power, and algorithms. I wanted to ask you, what do you think in the future? Will this trinity still, all pieces equally, we need to push on them to make progress, or is one of them very important? And what are your thoughts on that?
Yeah, I think that's a great question. And that connects to our recent conversation from neuroscience, right? And edge devices. I think in future, in addition to having large supercomputers and data centers, I think we'll continue in that realm. The other exciting piece is on the edge, right? How can we bring more intelligence to the edge? And with the Jetson and Xavier platform, broadly the EGX platform from NVIDIA, we have efficient ways to seamlessly move models into these edge devices and have good performance, the ability to work in low precision. I think we'll see more of that in future, right? These devices will get more and more miniaturized and be able to work with low power. And the nature of data will change. So far, we've used a lot of labeled data sets. So the question is multimodal data, right? Like other kinds of human feedback or continuous, right? Like signals. So thinking of all kinds of weak supervision or even self-supervision, right? Which has been very prominent in the last couple of years or more, where we see that in many cases it can even beat supervised learning, which is what our brains have been trained on. As infants, we don't have supervision. We are just observing the world around us and able to get robust representations. And the supervision only comes later once we are developing language. And so this aspect of training very effective representations with self-supervised learning, weak supervision for all kinds of more challenging image understanding and understanding of complex domains, I think is something we'll see more in the future. So, broadly, the Trinity picture still holds, but with the data, we'll see all kinds of other data and transformations of data, right, or augmentations of data. On the compute infrastructure side, we'll again see more diversification. We'll see all kinds of spectrum of edge devices and GPUs and other hardware for that. And also in the cloud, we are already seeing much more AI and HPC coming together. So the ALPS, which is the supercomputer that was just recently announced, will have NVIDIA Grace CPU and GPU together. So, we'll see much more tight coupling between CPU and GPU for efficiency at scale. And also, that'll be like 20 exaflops, but of AI computations, right? Whereas traditional HPC was 64-bit, very high precision requirement. So whereas now we are willing to work with lower precision, but have much more massive computing capabilities. So I think these are all exciting developments for this decade.
I see. Very exciting. Yeah, what's in store for the future is very exciting.
Thank you.
And yeah, it makes sense. I know a lot of other experts also are kind of proponents of unsupervised data or unsupervised learning, self-supervised as some of the big areas we need to push on to make big progress in the future. All right, I think we are out of time.
And Colin, if you want to quickly take maybe one question or from the audience, because we have around 14 of them.
Yeah, oh, I see. I didn't even see the Q&A. I was looking in the chat the whole time. Yeah, I was going to mention before the chat is very active in sharing the Tensorly notebooks and the books that Anima is mentioning. Okay, sorry about that. Yeah, I will. Now I see all the questions here.
Maybe just one.
Yeah, I mean, I'm sorry, and the links I can just after this I can quickly post on chat. So I'll go into the chat and post the links.
Mm-hmm. Okay, do you have any, I see a link to the book. Let me try to pick a question. Are there any use cases that would leverage deep learning with quantum computing?
Yeah, it's interesting that you ask. One of the projects we've been working with Tensorly is in the quantum machine learning realm, right? It's natural because, as I mentioned, my first introduction to tensors was quantum mechanics. So it's like coming back to that and asking how we can build efficient tensor representations to look at where there could be quantum advantage. I think quantum advantage is considered more nearer term compared to quantum supremacy, which is very hard to achieve. And so can we have low rank tensor representations that can be easily scaled up, right? That are easier to build and solve important problems, like global optimization problems, like different graph problems. Can we solve them with these kinds of quantum computers? So we've launched Tensorly Quantum, which is again a high-level API where you can easily define these tensor networks and quantum simulations with that. And with QQuantum, which is a low-level primitive, a CUDA-level primitive for speeding up quantum simulations, we can get very good end-to-end performance. And so we are able to do very fairly large scale simulations, even on one A100, right? So like 100 qubit simulations, but using these low rank tensors. And we can see like challenging problems like max cut, we can solve them very effectively using those. So I think that's very promising for near term quantum computing.
Nice, and that's a great full circle, starting with intuition and now using it to solve more problems. Okay, and I think a lot of these questions I'll be able to answer offline because they're asking about links or resources from the questions we went through. All right, so with that, I'll hand it off to Bindu. Thank you so much for joining us today, Anima. It was a pleasure talking with you.
Yeah, Anima, that was fascinating.
Thank you, Bindu. This has been a lot of fun and great to see you all. Eric, I also see you. So it's great to see you here and so many others. Yeah, have a nice day.
Thank you. And thank you so much for coming.